Welcome back. So, in the previous class we were in the middle of proving the important Sobolev lemma. So, we have derived this estimate. So, starting with the given function f, we defined another function on R n and we derived an estimate on this new function of this form, which is given by 2, and call this integral as j, okay, for the time being. Okay. Next, you consider this integral. So, consider this integral 1 plus mod y to the p, okay, f cap of y. I am not putting a square here, okay. And now you use, this is again R n, okay. So, use cos is what here. So, what I am going to put is this 1 plus mod y to the p as it is, and now I add this, you just recall here, this 1 plus mod y to the 2 m, okay, this 1 plus mod y to the minus m and 1 plus mod y to the m and f cap. Okay. I know this is in L2 because this just now proved it. Okay. So, you just get this is equal. Okay. Now, I use, I am not doing anything here. So, now just I get this 1 plus mod y to p minus m, okay, to the half, and this is j to the half. Let me not write that. So, we have already introduced that notation. So, this is j to the half. Okay. And what about this one, this integral? So, now we use that hypothesis 2 p minus 2 m, okay, just this you use spherical coordinates. So, you get a factor of n minus 1 there. So, just n minus 1, okay, and by hypothesis this is less than minus 1. So, because of this integral is finite. In fact, long back I asked you to compute that. So, it is in fact, I asked you this one. So, this is very easy to, you can express this in terms of gamma function or beta function. So, this one 1 mod y square minus k. Okay. So, this is an interesting integral for k large enough, okay, k large enough. So, you can actually compute that. So, this so for p bigger than or equal to 0, this integral is finite. Okay, so that's what we get. Okay, so the conclusion here is, so this 1 integral 1 plus to the p f cap y again in Rn is finite. So, since p is bigger than or equal to 0, in particular we have f cap is in L1. Just see this analysis, very clever analysis, okay, and okay. So, now that f cap is in L1, we can define its Fourier transform. Very interesting, right? So, that so f, you define f omega, because it is all started with that open set. Okay. So, just since from the beginning I have put this factor, let me again put it. So, this is again in Rn f cap y e to the I put I x dot y. So, this is actually inverse transform dy. Okay. This we can do because f cap is in L1. Okay. So, by inversion formula, so this we have already learned. Formula, this f of x is equal to f omega x almost everywhere. Okay. But this one we know it is continuous. Okay. And again go back now. So, if p is bigger than 0, so we get also some powers of y there, okay, and again we can take the they are all L1 functions. So, if you iterate this several times, okay, so by iterating or you can directly take the derivative of that is justified, because whatever y variable you get, they are all integrable functions, and that will be the Fourier transform of that L1 function. By iterating we see that f omega is actually C p. This is defined for all x, okay, that is no problem. So, this is a p times continuously differentiable function on Rn, fine. And further if omega prime is another open set with same property, that its closure is compact in K open set, okay. So, we obtain another Cp function f omega prime, but it is easy to see that. So, easy to see, they agree, easy to see that f of omega is f of omega prime on omega intersection omega prime. Okay. So, this way we can just define f 0 x as f of omega x if x is in this open set. Okay. So, we can always take a small ball around x and that is in omega. Okay. Since, so again just remember that f is psi f in omega, okay, and psi is 1 on k. Okay. So, this since psi is identically 1 on its support on k, okay, on k we obtain this f of x equal to f 0 x almost every. So, very nice proof indeed. So, it uses all the tools we have developed, namely on Fourier transforms and the derivative of the Fourier transform, etc. Okay. So, just one remark, I will just close this one, just one remark. So, we have this m is bigger than p plus n by 2. Okay. So, you put, so there is still some gap, that is what I want to mention here, m minus p minus n by 2. Okay. So, this is positive and it can go up to 1. If it goes beyond 1, so you put that in p. Okay. So, you have more smoothness. Okay. So, one can actually prove the one can show. So, but this is much harder work. One can show that the highest order derivative. So, namely this I f, you take mod alpha equal to p are Hölder continuous. So, you have to verify the hypothesis one puts on omega and other things, but essentially so this whatever gap is there, so that gap also gives a kind of smoothness, continuous with index alpha. Okay. Okay, sorry, there is alpha alpha. Okay, so let me change it. This beta. Okay, so this, let me erase that. Beta. I am not sure. Maybe it is due to Moray, okay, but I am not quite sure. Okay, so, just check the literature. So, even this little gap gives us some smoothness of the highest order derivatives. Okay. So, we have not defined those spaces, but they are generally denoted by Cm alpha. Okay. So, smoothness plus some Hölder continuity, Hölder continuity of the highest order derivatives. Okay. So, with this remark, now I just want to do one last thing. So, in fact, in one of the previous classes I stated this. So, let me just again state it. So, theorem. This H1 0 omega is precisely all those u in H1 omega such that trace is 0. Okay. So, our definition of H1 0 omega is the closure of C1 functions with compact support. Okay, omega or omega closure does not matter because we are putting compact support in the H1 R. Okay. So, I remark that this proof is somewhat very technical. Okay. So, I try to sketch it. Okay. So, this proof. Okay. So, let me begin with. So, this actually requires a kind of continuity of the trace. I will try to make it more clear. So, that is the preparation, that is the actually preparation. Okay. So, here we have this omega. Okay. So, before coming to the actually this is not proof will come little later. So, this is del omega, and now you consider any surface. So, it can be this boundary, but generally we work for any surface. Okay. So, some surface. Sitting in omega. Okay, this is omega. Okay. So, let me write that. So, this way in fact, we have done to some extent when defining the trace. So, I am doing the same thing again. So, let gamma 0 be a small simple piece. Okay. So, just recall the definition of the simple piece. So, small here it refers to it can be embedded put in a small ball. Okay. So, this gamma 0 is contained in some ball of radius r. Small radius. Okay, let me write that. So, that is what small refers to, simple piece. Okay. So, so again I am going to assume that, so this of class C1, okay, simple piece of class C1, that is okay. So, gamma 0 is given by this equation. Again, for simplicity I chose this variable. So, we can write this. So, x prime is in D. So, this is the projection of gamma 0 onto this plane, x n equal to 0. Okay. So, this we did elaborately when discussed the trace, and phi is a C1 function defined on this closure. Okay. So, that is what class C1 refers to. Okay. So, for small delta, positive or negative, it does not matter, for small. So, let me just write this. So, this gamma 0 is somewhere. Okay. Small delta, let gamma delta is given by so this is just a translation. Okay. So, this is also a simple piece of class C1, because this I am just adding a constant. So, this is also a C1 function, again x prime is there. Okay. So, you can call this as, depending on whose side and this function delta positive or negative, let for just, so it is a parallel, it can be above also. Okay, that is no problem. So, parallel. So, this is parallel surface. Okay. And now, you define this q delta. So, essentially this space between these two surfaces. So, this is q delta. Okay. So, q delta x prime x n. So, x prime is in D. So, it is easier to understand from the figure. Okay. So, that is, so phi x prime is less than x n less than a small region sitting between these two. So, if delta is positive, because we are using inequality here. So, if delta is negative, you just change it to phi x prime plus delta less than x n phi x prime. Okay. So, remember these are all in omega. Okay, I forgot that, tell that. So, they are all in omega, these surfaces. Okay. So, for delta small, one of them, okay, this either q mod delta or q minus mod delta is in q omega. So, that you can easily see if the gamma 0 piece is on the boundary. Okay, so for example, this del omega and gamma 0 is just piece here, okay, and then you have the parallel piece here and this sitting here. But if the parallel piece we take outside, then that portion will not be in omega. Okay. So, we are interested in the piece where it is in omega. Okay. So, now for definiteness sake, so we will put it. So, for definiteness, we assume that q delta is in omega, q delta is in omega and delta is positive. The arguments are similar if otherwise. Okay. So, there no problem. So, now assume, so these computations we have done earlier also, f is in C1 omega closure. Okay. Then by the usual calculus, I will just write this one and just stop there. P x prime is equal to P x prime P x prime. The same thing what we did while discussing the trace. Del x n x prime x n. Okay. So, now take the absolute value and use again Cauchy-Schwarz and multiply by. Okay. So, take absolute value. So, I will just absolute value, use Cauchy-Schwarz. Okay. So many steps you have to do, and then you multiply by this factor by 1 plus grad phi square and integrate over d. Okay. So, similar calculation we did while discussing the trace over d. Okay. So, let me just write that the final one. So, this f of x delta minus f of x 0 L2 gamma 0, okay, less than or equal to some constant. So, let me just write delta we are taking positive. So, there is no problem there, H 1 q delta. Of course, there is no difference between gamma 0 and gamma delta, because just translation is taking place there. So, this is obviously valid even if you replace this by L2 gamma delta. Okay. I will stop here. I will continue from this point next time. Okay. So, I just want to show how that condition that trace is 0 is reflected in this L2 integral. Okay. So, that is the first important step, and rest is somewhat simple. Okay. So, finally, we have to get a approximation from a C1 function with compact support. So, that is our goal. Okay. So, we will continue in the next class.